Alright, so in this video we're going to figure out how to find the electric field on some point on the perpendicular bisector to a segment of uniform charge. So let's say that the length of this segment is L, and let's say that our point of interest is a height D above the segment. Again, we're sitting on the center line here. Okay, these kind of problems, the usual strategy, is to identify a differential chunk of charge right here, dq, and we figure out its contribution to the electric field strength. dE. So we'll just assume that the differential charge is positive. If it's negative, it'll point the other way. And all this will get taken care of automatically by the sign of the actual charge, which we'll say is Q. Okay. Now, in doing these sort of problems, the first idea is you want to exploit as much symmetry as you can. Since we're on the perpendicular bisector, we know that for every chunk of dq out over here on the left where I drew it, there will be a matching chunk on the right over here that will give a contribution pointing at the same angle and the same length, but to the left. So that means the right and the left contributions will cancel out, and we'll only need to consider the y component of the electric field. So it's dEy, and just for completeness, this is dEx, but the dEx contributions will cancel out once we integrate over all of our charge dq. All right, so first off, we can go ahead and write an expression for the magnitude of our electric field, differential electric field strength dE. We can write that as 1 over 4 pi epsilon naught dq. That's the charge at this point here. And now we need to go ahead and define some variables because we need this distance right here, this hypotenuse squared. Looking ahead to when we actually go ahead and take the integral over this, it's going to be natural to define the perpendicular bisector to be at x equals 0. So everything to the left will be negative x, and everything to the right will be positive x. So we'll say that that's our distance, that's our coordinate x right there. It won't really matter because we're going to square it anyway. Okay, so this distance here now is going to be the square root of x squared plus d squared. And then we need to square that as part of the whole kq over r squared thing. So this will be just x squared plus d squared in the basement there. All right, but that's for this piece right here, dE. And what we really need is this piece here, dEy. Okay, so a trick that we can do here, if you prefer writing this out in terms of trig functions, you can certainly do that. But I find that it's often easier just to go ahead and rely on the fact that this vector triangle here is similar, this vector triangle here is similar to this physical triangle here. So the ratio of the lengths of the corresponding sides will be the same. So we can go ahead and observe that dEy is to dE as, okay, my dEy will be like d here, And my dE will be like this distance here, root x squared plus d squared. So dEy then will be equal to dE times d over root x squared plus d squared. And so our dEy would be equal to, putting in for the dE, 1 over 4 pi epsilon naught d times dq over. Now here we had a square root of x squared plus d squared here. We're going to be timesing it by a x squared plus d squared there. So that's going to give me x squared plus d squared to the 3/2 power. Okay. Looking ahead further, to get the electric field strength, which we know the electric field will point straight up, we can just go ahead and draw that in right now because we know that that's what it's going to do at that point. We know it's going to point straight up. So when we integrate, we will be able to write that E is equal to EY is equal to the integral of this stuff. All right, so that'll be 1 over 4 pi epsilon naught d. Now we're left with integral dq over over x squared plus d squared to the 3/2 power. But although in principle you can integrate over this dq, we really don't know how to do that usually, unless we can turn it into some distance variable in most cases. But we can rely on observation here, and this is where kind of thinking about the calculus as a physicist becomes a little helpful. This differential charge dq has a width dx. And to a physicist, when we look at differentials, we usually just think of them as really tiny deltas, and this integration corresponds to summing up over the really tiny deltas. And actually this idea can be made mathematically rigorous, so it's not even a cheat to think of it this way. So since the charge is uniform, we know that the charge density here, dq over dx, has to be the same as the charge density for the whole thing, which is q over L. So then I can express my dq as q over L dx. Okay, that's going to allow me to go ahead and properly set up the integral. So we now have that the electric field strength will be 1 over 4 pi epsilon naught. All right, so we've got a q, a d over L, pulling out the constants. Now we're left with integral dx over x squared plus d squared to the 3/2 power. And we need to think about our limits of integration. Since we chose x equals 0 to be at the perpendicular bisector to our segment of charge, the left-hand side will have a coordinate of minus L over 2, and the right-hand side will have a coordinate of plus L over 2. So that's going to be our limits of integration. Okay. Now, the way that any good integral gets worked out in physics, honestly, is to look it up or use Mathematica. So let's go ahead and use Mathematica right here. If you're asking a computer to evaluate these sorts of integrals, a program like Mathematica is going to try to do everything as generically as it can. It's going to assume that our x, our d, and our L could have any possible value, positive, negative, 0. In fact, even including complex values. So you can add pieces that are multiplied by the square root of -1. It will eventually find the integral, but a lot of times it's a lot faster if you just give it the hint that these are all positive numbers, and then go ahead and tell it to integrate it. So we go ahead and do the integral, and we see that is 2L over d squared times the square root of 4d squared plus L squared. Okay, let's go and put that in. So now my electric field strength is 1 over 4 pi epsilon naught qd over L, and then we put in what the integral evaluated to. That was 2L over d squared times the square root of L squared plus 4d squared. All right, we can cancel these L's and 1 power of d there. That's about as much as we can get cleaned up. And we can get this into a little more bookish format if we divide numerator and denominator by 2. If we do that, you end up with 1 over 4 pi epsilon naught times q over d times the square root of d squared plus L over 2 squared. And that's our answer. Now, before we say that we're totally done here, it'd probably be a good idea to do some basic sanity checks. 1, do the units check. Well, let's work that through, huh? So 1 over 4 pi epsilon naught, that's also K. That has units of Newton meters squared per coulomb squared. We're going to times this. Okay, we got an electric field there. So this is going to be units of coulombs. And then here we've got 1 power of meters there. Then we're going to have the square root of meters squared plus meters squared. So okay, when I add meters squared together, it's still meters squared. Then when I take the square root of that, that's meters. So that square root cancels one of these power meters. This one cancels that. We lose 1 power of coulombs there, and we're left with newtons per coulomb. Yay, that's the units of electric field strength. So we would hope that that would work out. Then the other sanity checks that we should do would be to ask what happens at the limit in the limiting cases. Now, thinking about the limiting case where d is really small, that would be basically putting you right on top of the charge distribution. You would expect the electric field strength to be infinity, and sure enough, as d approaches 0, this denominator is going to approach 0. The electric field strength is going to go up to infinity. That makes sense. But more interestingly is what happens if d becomes really large. And whenever you say large in physics, you always have to say compared to what. And there's always something in the problem that will set a natural scale length for the problem. In this case, the natural scale length here will be the length of my line of charge to begin with. So if d is really large compared to L, let's see what that looks like. So we'll say if d is much greater than L, then my electric field strength will be 1 over 4 pi epsilon naught q over. Now I'm going to have a d, but now let's look at this root here. If d is really big compared to L, d squared is going to be a lot bigger than L squared over L over 2 quantity squared. So this term is basically going to wash out, and I'll be left with a square root of d squared, which is a d times that d there. Hey, that's kq over d squared. That's going to be the electric field strength due to a point charge a distance d away. And that makes sense. If d is really big compared to L, you're getting to a point where you would have a really hard time telling if you're looking at something of a finite extent, and so you would expect the answer to converge to the point charge. So the units check and the limits check, so we have great confidence that this is indeed the correct answer.